Let's do another example. A ski gondola in Bogus Basin Ski Resort carries skiers to the top of the mountain. Assume that it bears a plaque stating that the maximum capacity is 12 people or 2,004 pounds. That capacity will be exceeded if 12 people have weights with a mean greater than 2,004 divided by 12, which is 167 pounds. Because men tend to weigh more than women, a worst-case scenario involves 12 passengers who are all men. Men have weights that are normally distributed with a mean of 172 pounds and a standard deviation of 29 pounds. So our question is, our first one here, again, is no different than what we learned in the last lesson. We just simply want to know what's the probability if I selected a guy at random from the population of men out there that his weight would be greater than 167 pounds. So the reason the 167 keeps coming up is because they took, again, the 2,004 pounds that the gondola can hold and tried to share it evenly among 12 people. So that means each person would weigh about 167 pounds if they're sharing the 2,004 pounds equally. So we want to know in general, what's the probability that a guy out there weighs more than 167 pounds? Let's figure that out. So here is our normal model. You can see the 172 that was mentioned in the previous slide and the 29 pounds as the standard deviation. So each tick mark is 29 pounds away from the next, just to give a nice labeled model here. And the 167 we're curious about is just to the left of 172. So this red region, again, we said would weigh more than 167 pounds. This red region is our solution. In order to capture how much this is of the curve, we need to turn our data into a z-score. So we're going to take the 167, subtract off the mean of 172, and then of course divide by the standard deviation of 29. If you poke that into your calculator, you'll discover that the z-score is negative 0.17. Not surprising. Look how close 167 is to 172. Just a fraction of a standard deviation to the left. We're going to visit our z-table or go to software, and you'll discover that when you look up negative 0.17 as a z-score, it'll give you 0.4325. Now remember, we are shading to the area to the right here. So the 0.4325 is actually this white area on the left that we're not all that interested in. In order to get the red area, we take the information we got from the z-table and we subtract it from 1. So what this tells us is that the area to the right is 0.5675. So that in turn gives us that there's a 56.75% chance that a randomly selected man would weigh more than 172 pounds. So almost a 57% chance if you randomly picked a guy from our population here in America, he would weigh more than, whoops, I shouldn't say 172 pounds, there's a typo there, would weigh more than 167 pounds. So I'll make sure I change that. There we go. Sorry about that. Okay, here's the next part of this problem. This is the part that we're really getting at because of the ski gondola. We want to find the probability that 12 randomly selected men will have a mean weight that is greater than 167 pounds. And the reason, again, we're interested in the 160 pounds is that if each of them weigh on average 167, or their average weights are 167, then it would be greater than what the gondola could hold. So it kind of puts it on that dangerous spot of it exceeding the maximum capacity. So we want to know, what's the likelihood of that happening? Well, first, what we need to do, because we're not just looking at one guy anymore, we're looking at 12 men, we have to take our standard deviation of 29 and divide it by the square root of 12. And that reduces it down from 29 pounds to 8.4 pounds. You guys are getting to see me do some editing here. That looks better. All right. So we are going to take and create another z-score. Now again, as I've mentioned every time before, each of these tick marks are 8.4 pounds apiece because that's what our standard deviation is, been reduced to. 167 fits right in between 172 and 163.6, so it's just to the left here. And if we turn that into a z-score, so that we can check the z-table, we get a z of negative 0.60. Yet again, go to the z-table, look that up, and the z-table will reveal an answer of 0.2743. Keep in mind, it always gives you area to the left, so that's the white region we're not interested in. We're interested in how big is the red region. What is the size of that region? And that size of that region we can turn into our probability. So if we subtract the 0.2743 from 1, it gives us the other side, the red region, which is 0.7257. So there is a 72.57% chance that the mean weight of 12 randomly selected men would be more than 167 pounds. Sorry about that. So you can see it's quite likely that if you get 12 guys on the gondola, there's a 70% chance they're going to exceed the maximum capacity. I wouldn't be so comfortable with that, getting on a gondola or being one of these gentlemen per se. It's a high probability that the maximum capacity, as far as pounds are concerned, would be exceeded. So you have to kind of wonder why this is the case. My hunch is that this is an old gondola, and the standards that were put on it for the placard are based off of the mean weight of people of decades ago, and I think we all agree that in the past, recently, we know that our American population is getting heavier and heavier, so possibly that's why there's such an easy chance for this to be exceeded. And I would imagine that somebody would want to look into this and definitely change the placard. I don't think you can change that it's 2,004 pounds. That's essentially what the gondola can hold. We would definitely want to figure out how many people would that be with the way our weights are distributed now in the recent times. So anyhow, it's an interesting problem. You can see the difference between the first part and the second part was 1 person versus 12, and thus that's why we divided by the square root of 12. Now, what I want to do last here is to illustrate this idea with one of our applets in StatCrunch. So I'm going to go to Open StatCrunch. The applets, we were here before, we're going to the sampling distributions, and I'm going to use a bell-shaped one, and our mean was 172 pounds, and our standard deviation was 8.4. No, actually no, we take that back. 29. So this is just the general thing we were told by in Haynes at the beginning of the problem, that men on average have a weight of 172 pounds and a standard deviation of 29. So there's our population of men right there. Just general population out there. So what I want to do is pick a sample of 12. And you saw me do this at the beginning of the lesson or the beginning of the module. And let's see what the first sample is. I'm randomly picking 12 guys out. So here they are. And these 12 guys have a mean weight, all their weights added together divided by 12, of 189 pounds. Looks like the gondola is not going to be okay. Now, keep in mind there's 70% chance that these men's weights will exceed this. So 7 out of 10 of these that I sort of simulate here probably will have a mean that's too heavy. Let's try another one. Oh, so we can see here 12 men randomly selected. The mean for this one is 165.6. So this gondola, these riders are safe. Their mean weight is under the 167 pounds. Let's try it again. Oh, well, just barely. These guys are right under 170 pounds. So the third sample, unfortunately, exceeds that. So I don't know how safe the gondola is. Try it again. 175 pounds. Bye-bye gondola. Again, you can see over here, 179 pounds. Bye-bye gondola. Not looking good. Heavy. Heavy. So if I continue to do this over and over, and I'm not going to bore you. Oops, there's one that survived. So you can see now we've done it a little over 10 times. We've had a few times where the mean weight of these randomly selected gentlemen is less than 167 pounds. But more times than not, it's going to exceed it. And the safety of the gondola is in question. There's a really light group of men. They average out at 156 pounds. So again, about 7 out of 10 times the gondola weight limit will be exceeded. That's what the 70% means. I hope the simulation helped.